So let's discuss further the properties of fluids. So in my separate lecture, Engineering Thermodynamics, I already discussed the properties of matter. So like mass, volume, weight, temperature, pressure, specific weight, specific gravity, etc. But then I will discuss this again and add some properties of matter that is important in the study of fluid mechanics. So let's start with the mass. So take notes, mass is the quantitative measure of the amount of matter in a given body, or it is the absolute quantity of matter. This means that the mass doesn't change at all regardless of position, temperature, pressure, etc. So let's say, for example, we have a mass inside a system. Okay, let's consider this as closed system. So when we add heat here, creating temperature and let's say pressure to rise up, we can consider, since this is a closed system, we can consider that the mass is constant regardless of change in temperature and pressure. Similarly, when you have a body, for example a human body here in Earth, okay, so at sea level, okay, wherein the gravitational acceleration is 9.8066 meters per second. When you bring this human body, okay, to the moon, for example, okay, moon, and ask what will be the mass, we can say that this will be the same. This will be a constant. If you have a mass here at sea level of 70 kilograms, the mass here in the moon will be the same, 70 kilograms. So mass is absolute quantity. It doesn't change regardless of pressure, temperature, position, location, etc. Okay, so that's the mass. And then property number 2 is the weight. That is the force of gravity on the body. We normally abbreviate it as W or Fg, wherein based on the second law of Newton, we have weight equals to mass times gravitational acceleration, and K is basically the proportionally constant. Okay, so G value at sea level again is 9.8066 meters per second. And then third property is the density. Basically, density is the mass over the volume of a substance. So again, this one is the density. Sorry, it's here. And then mass over the volume. So the value again of G at sea level is 9.8066, and then 32.174 feet per second squared for English system. So for fluids, so let's discuss this further. So for fluids, take note that the density is dependent on the temperature. So here I have a simple illustration. In the vertical axis, I have the density of water. This one is H2O, okay, and then here in the horizontal axis I have the temperature. On this side I have again the density and then the pressure. So I mentioned that the temperature or the density of the body or a fluid is dependent on temperature. Okay, so as you can see in here, there's a value we have here around 50, 100 and 150, from 1000 to somewhere 950. So as you can see, as the temperature change, okay, so here we have 50 and then 100. So the value of density is also changed. So it means that at higher temperature, the density of the liquids, or in this particular case H2O, is less, okay, at higher temperature. And if we look here and observe the effect of pressure towards the density, we can say that the pressure has a very minimal effect on the density. So to multiply the density or to reduce the density from 900 something to, let's say, 1008, we have to multiply the pressure by 200 times. So 200 times, which we can say that this one is negligible. Okay, negligible. So next is the specific gravity. So specific gravity, also known as relative density, is the ratio of density or the specific weight of a substance to the density of the specific weight of some other standard substance. In this particular case, H2O. Again, the reference substance for liquids like water, mercury, or even solid is the water, wherein we take a density of water at 4 degrees Celsius at 101.325 pressure kilopascal or 14.696 psi. So we take this as 1000 kilogram per cubic meter. That is the standard density value of a substance. Okay, now for air or for a gas, we normally use air as a reference, wherein we use, I can write it here. So let's say for gas, our reference is air. Okay, gas. Okay, so again, specific gravity is density of a gas over the standard. Again, we use the air here. What is the density of air? That's the question. So we learned from thermodynamics this relationship, PV equals to mRT, and then based on this formula, density is mass over the volume. Okay, this means that mass over the volume is P over RT. Again, our standard reference here is the pressure and temperature. R is a constant. It's the universal gas constant. So for air, density of air, we can use the standard condition at sea level, 101.325. This one is kilopascal, and then R is 0.287 multiplied by the standard temperature at sea level is 21. So this one is plus 273. And here we can get approximately 1.18 kilogram per cubic meter. Again, we use this as a standard density for air at sea level as a comparison in terms of calculating specific gravity. So this values, this 1.18, or sometimes other books 1.2 kilogram per cubic meter, is very important in calculating the specific gravity of a substance. So we take it here, 1000. Specific weight of water, which we will discuss later on, is 9.8066 kilonewton per cubic meter, and the density is 1.18 kilogram per cubic meter. Okay, so here I forgot, if we zoom this out, this part here, this is the density again, and temperature, as you can see, at 4 degrees Celsius, okay, the maximum or the value of density is approximately 1000 kilogram per cubic meter. And then as we move towards here, let's say at 0 degrees Celsius, the value is 0.9998 or less than 1. Okay, this means that this one is ice point, 0 degrees Celsius. The water will become solid in this condition. This means that the ice will float if you mix water, okay, and this ice, let's say solid, it will float because the specific gravity, as you can see here, is less compared to the water. Okay, so normally this is the reason why iceberg floats also in the ocean. Okay, so and if you go further towards here, as you can see, the density of the liquids also, or the water, is also changes. Okay, so here I have a simple illustration also for specific gravity. This one is an experiment with an egg and a water. So this one is a normal, no salt. Okay, no salt. So as you can see, the egg sinks to the bottom. Okay, and then if we add salt here, okay, also here, as you can see, the reaction of the egg. So this again the reason why the ice flows in the water, because first of all, ocean of course is salty, and then since ice has a less specific gravity compared to the salt water, then therefore the ice floats in the ocean, or the iceberg floats. Okay, let's move forward now with the specific weight. So specific weight is a weight per unit volume. So again, we denote it like this. specific weight, weight per unit volume. So we can derive this further. So specific weight, weight per unit volume, and take note, weight is what? Mass over G, mass multiplied by G over K. Again, K is only a proportionally constant for unit cancellation. And then with this, we have specific weight is mass multiplied by G over K. Again, this represents W, and then over the volume. And as we know, mass over the volume is density, and therefore the specific weight is density multiplied by G over the proportionally constant K. And then we have the specific weight, specific volume, that is the volume per unit mass of a substance. It is the reciprocal of the density. It's quite obvious. So again, specific volume is volume per unit mass, or simply 1 over the density.